Hey guys, this is going to be our final video for chapter 6, kind of combining concepts from 6.8 and 6.9. Kind of foreshadowed it at the end of last video, but how do we find zeros if we aren't given anything and if our pre-existing strategies aren't working out too well? So here's what we've got. At the start here, again, it's so important. I know I had this in bold and underlined before too. But we will find the number of zeros to be the same as the degree of the polynomial every time. That includes real zeros and complex numbers. But if it's an x to the 5th, we can expect to find 5 zeros total. If it's x to the 1st, we can expect to find 1 0 total. Now, there's a theorem up on the screen here, the complex conjugates theorem, which is something you might have picked up on already. But again, I like to formalize it and say, yep, you might have had this gut feeling, but it's definitely true. The complex conjugates theorem says if a plus bi is a solution, is a root, is a 0, then a minus bi has to be one as well. They come in pairs. So a plus bi, a minus bi. On the screen here, I have a problem that I worked at the end of the 6.6 video, solving x cubed plus 8. And so it was a sum of 2 perfect cubes. So used that formula and got x equals -2 in red, super easy. The other one, this time in the 6.6 video, I used completing the square. Here, I just wanted to demonstrate we could use quadratic formula. And so if you look at the work there, you'll notice we end up with 1 plus or minus I root 3. And that's kind of the reason this theorem holds, is because anytime we have I, it means we were taking the square root, right? Square root of a negative. And anytime we have a square root, that means we have plus or minus. So this is why this theorem holds, saying if there was a plus I part, there was a minus I part as well. If a plus bi is a solution, a minus bi is also a solution. 1 plus or minus I root 3 in that case. So they come in pairs, which is kind of super handy to know. But that's not the meat of this lesson. The meat of this lesson is right here. There's a lot going on in that yellow box. I stole that graphic from your textbook. I don't need to write it down perfectly and anything like that, but I want to just point out a couple things. Then we're going to demo, and we're going to walk through it kind of slowly and show you how this works. So the rational zero theorem has to do with these P's and Q's. Okay. It says that if there is a rational zero, rational meaning it can be expressed as a fraction, 0 meaning solution, then we actually, there aren't an infinite number of possibilities as to what those zeros could be. Here's how it works. We have a polynomial here, I'm highlighting in yellow, 2x cubed minus 11x squared plus 12x plus 9. Now, you might say, how should I just find the zeros by guessing? I mean, like, it could be anything. Well, actually, it can't. Here's our process for finding possible zeros. And you have some homework problems that don't even ask you to solve anything. Just practice finding those possible zeros. P is going to be the set of all factors of, in this problem, 9. All factors of our constant. So what times what could equal 9? Well, 1 goes into 9 evenly, 2 doesn't. 3 goes in evenly, 4, 5, 6, 7, 8. 9 goes in evenly. 1 times 9 or 3 times 3, right? And it does say list all possible rational zeros. They might be negative. So we also have to include, well, it could be -1 times -9 or -3 times -3. So P is the set of all of the factors of our constant. Okay, so in this case, 9. Q is the set of all factors of our leading coefficient. In this case, our leading coefficient is 2, so there aren't that many factors, plus or minus 1, plus or minus 2, because 1 times 2 is the only way we get 2. And so this right here, what I have highlighted up top and circled in green, it says if P over Q is a rational number, then P is a factor of A naught, that's our constant, and Q is a factor of A sub n, that's our leading coefficient. That means we can list out all of the possible zeros after finding P and Q by just having all different combinations of the P's over the Q's. So for example, possible zeros, plus or minus 1 over 1. So I'm just going to write that as 1, because 1 over 1 is 1. Plus or minus 1 over 2. We're just going to take every P and put it over every Q. Okay, so plus or minus 1 over 1, plus or minus 1 over 2, plus or minus, let's take our 3 over 1. So plus or minus 3 over 1, I'll just write that as 3. Plus or minus 3 over 2. And then the last P, plus or minus 9 over 1. So 9. And then plus or minus 9 over 2. And guys, it might not seem like much, but that's actually a really significant result. Before we did this, we would literally have to try an infinite number of zeros if we were just shooting in the dark. Now we are saying that if there are any rational zeros here, they have to be one of these. 1, 2, 3, 4, 5, 6 times 2 because of the plus or minus. They have to be one of these 12 zeros. Now, trying 12 things, it still seems like a lot, but it's way better than infinite. So this is how we can list all possible zeros, all possible rational zeros, I should say. So same thing here, make your list of P's and Q's. Then put all the P's over all the Q's and find our possible rational zeros. Repeat those steps for me. Pause the video, just make sure you can do it on your own, find any questions you have, then unpause this video and see if you were right. All right, so I've gone ahead and listed out my P's and Q's. P's were all the factors of my constant, 10, so plus or minus 1, 2, 5, and 10. Q, all the factors of my leading coefficient, 3, so plus or minus 1, plus or minus 3. And then just like above, and I added a little note up there, we're going to get our list of possible zeros by doing every P over every Q. So I haven't done that yet. Let's do that one together and then make sure that you agree your work matches. So if I'm looking for all the P over Q's, well then all the possible zeros are plus or minus, let's just go down the line like we did last time. 1 over 1, so 1. 1 over 3, so plus or minus 1/3. Now we go on to the next P, 2 over 1, plus or minus 2. 2 over 3, 5 over 1, 5 over 3, 10 over 1. So I should just write that as 10, and plus or minus 10 over 3. And now we've found all possible rational zeros of that polynomial. This is not useful in and of itself, but it is going to be useful here with this next problem. So if your work matched mine, if you got those same possible zeros, awesome. Go ahead, just move on. Because now we're not just going to list all possible. That's just step 1, you'll see. Now we're going to use synthetic substitution to take our possible zeros and find which one of them is actually a 0. And then once we know which one is actually a 0, we're going to divide it out and see if any of our factoring methods work well. So you can see k of x is a quartic. It has 5 terms, so that doesn't lend itself well to grouping. It's not a sum or difference of 2 perfect cubes. It's not a typical chapter 5 one. I don't know how to attack this one, so I'm just going to use kind of this catch-all method. It says find all real zeros, and then I'm also going to change this and say we will also find the complex ones at the end, just because I want you to. So step 1, list all possible zeros. I'll keep the steps on the screen for now. So all possible zeros, what we were just doing, P is going to be the set of factors of our constant 18. So plus or minus 1, plus or minus 2, plus or minus 3, not 4, not 5, plus or minus 6, plus or minus 9, plus or minus 18. Those are all the things that can multiply to be 18. Q's are going to be all the factors of my leading coefficient. So plus or minus 1, plus or minus 2. Awesome. So then what about P over Q? P over Q is going to give me all my possible zeros. So plus or minus 1 over 1 is 1. Plus or minus 1 over 2, 1/2. Plus or minus 2 over 1, 2. Now, plus or minus 2 over 2, if I'm doing that P over that Q, that would simplify to just 1, which I already have in my list. So I actually don't have to put down 2 over 2, because I already have it in my list. So let's just move on. Plus or minus 3 over 1, plus or minus 3 over 2, plus or minus 6 over 1, plus or minus 6 over 2 would get me 3, which I already have in the list, so don't need to list it again. Plus or minus 9 over 1, plus or minus 9 over 2, plus or minus 18 over 1, and 18 over 2 would be the same as 9. So that's my list of all possible zeros. Again, way better than infinite. Still maybe more than we like, but way better than infinite. So that was step 1. We listed all the possible zeros. Step 2 says use synthetic substitution to find 1 0. So here's what this is going to look like. We're going to use synthetic. I'm going to set it up pretty much the same way, but I'm going to draw it slightly different just to save some room. So I'm still going to make a top row of, just make sure I have lots of room. Still going to make a top row of my leading coefficients of my polynomial. So 2, -5, 20, -45, and positive 18. So here's what I'm going to do though. I'm going to have to write this out probably multiple times, chances are. So I'm just going to make a table, and we're going to kind of omit that bottom row, or the middle row, I should say, of synthetic substitution. We're going to do that part in our head, and I'll show you what that means. But here's what we're trying to do. We're trying to find a 0. We saw in the last video, in the 6.7/6.8 video, if we plug it in, synthetic substitution, and if we get 0 as the remainder, it is a factor. So we're just going to plug these in until we find one that gets 0 over here in that last column. Then we know it's a factor, we divide it out, and we can use our other strategies, hopefully, on our new polynomials. So my advice, always start with the easy stuff. Always start with the easy stuff. So I'm just going to start with positive 1, and maybe I'll get lucky. So think about synthetic substitution. The 2 comes straight down. We keep that row. But then we're just going to say 2 times 1 is 2, and add it to -5 straight away, getting -3. And that's the row we're skipping, is that second one that we add. But hopefully we've done this enough that we're feeling pretty good about it. Now we say -3 times 1 is -3. Add it to the 20 straight away, we get 17. Times 1 is 17. Add it to the -45 straight away, we get -28. 1 times -28 is -28. Add it to 18, we get -10. This was not a 0. So, okay. What else should we plug in? I would vote, I said keep it easy. I wouldn't do that 1/2. I would do either -1 or +2. I like positive numbers personally. I'll try plugging in 2, and we can use this same table for the same method. That's why we kind of left out that middle row. So 2 comes straight down. 2 times 2 is 4. Add it to the -5 right away. That gets us -1. -1 times 2 is -2. Add it to the 20 straight away. That gets us 18. 2 times 18 is 36, add it to the negative 45 straight away. That's negative 9. 2 times negative 9 is negative 18. Add it to the 18 straight away, and we get 0. Guys, 2 is one of our zeros because we got 0 over there for the remainder. That means when we plug it in at 0, it is a root. You might have to do more than 2 of these on problems. You might have to do 3, 4, 5, but usually if you plug in the positives and the whole numbers, you'll find one fairly quickly. And then we don't have to just keep plugging in to find all the others. Now we have a new polynomial. We started with x to the fourths. Now this means 2x cubed minus x squared plus 18x minus 9. And now I can say, do I have any strategies that would work to factor that? I'm gonna fix that 8. Do I have any strategies to work? Well, it has 4 terms. Let's try grouping. And so we could pull out an x squared times 2x minus 1. We could pull out a 9, a positive 9, leaving us with 2x minus 1. So this is good. I can factor it, x squared plus 9 times 2x minus 1. Why am I factoring? I was tasked with finding all the zeros, real and complex. I found one of them, 2, but I started off with x to the fourth, so I know there should be 4. Fortunately, I think I can see another one that'll come out of here. 2x minus 1, what would make that equal 0? If x equaled 1/2. So now we have 2 of our 4 zeros. The other 2 I need to say, okay, well, what would make this equal 0? X squared plus 9 equals 0. We could say x squared equals negative 9, which means x equals plus or minus, if we square root both sides, 3i. And guys, now we have all 4 of our zeros. We knew we needed 4 because it was x to the fourth. And so our zeros, we found x equals 2. We found that in the table. That was the first one. 1/2, we found by factoring and then setting 2x minus 1 equal to 0. And plus or minus 3i. And those are the solutions to this graph, to this function. Now, as you can see, these are kind of extensive functions. These are kind of extensive problems to work. You got to list all the zeros. You got to make your table. Sometimes you got to plug in a few values, 3, 4, 5 values before you find your first 0. You've divided it out, so you take what's left and you try to factor it and solve it from there. But this gives us a method. Like I said, it's kind of a brute force method of just trying things. So it's not what you should start with on a lot of problems. This is kind of a last resort. But it does give us a way to find all the possible zeros and then plug them in until we find one, divide it out, and solve that simpler problem. So this is the only full example we're doing on this. If you need to, rewind and watch this over again. It'll make more sense the second time. If you need to, rewind it, watch it over a third time. But then try your practice problems. Try your practice problems, compare with the answers that I've given you, and see if this method is coming out okay, if you're understanding it and feeling good about finding those zeros. But guys, if none of our other strategies work, this is a great way to at least get a foothold and try to find at least 1 0 of a x to the fourth, a quartic function. And then from there, just see where it leads you. It will probably be easier to find the remaining ones afterwards. Guys, that's all I've got for you today. This is the end of chapter 6. Work on those practice problems. Ask me questions when next we meet. And I will see you then.